Today we'll look at finding probabilities of compound events, and in particular we're looking at situations where events either overlap or are what are called mutually exclusive. So if we have two different types of events, sometimes they share results in common and sometimes they don't, and that kind of dictates to us how we calculate the probability of those events happening. So two events that have outcomes in common are known as overlapping events. If they have no outcomes in common, then those are disjoint events, or what are known as mutually exclusive. So you've seen Venn diagrams drawn. So for instance, in this example, you have the group of people that are angry, and you have the group of people that are superheroes. And in that green area, the overlap between angry and superhero, that might include the Hulk. We have a group of people that are angry and a group of people that are British. The overlap in there might include Gordon Ramsay. So these would be examples of overlapping events. A look at that visually gives you the union of A and B, including all the items that are in either A or B. The intersection includes only those things that are in both A and B. And when events are disjoint, there are no events that belong to both circles. So the way that we calculate probability of these compound events depends on whether they are overlapping or not. So if we have disjoint events, the circles are completely separate, mutually exclusive, so we calculate the probability of event A and event B happening, and then add those two things together. If we have overlapping events, we can add together A and B, but we also have to account for the fact that there might be some that are in the union, and we want to avoid counting those things twice, so we actually separate out the probability of things that belong to both groups. So let's take a look at an example. So the first is the mutually exclusive case, where we've got a card that's selected from a deck of 52, and we want to know what is the probability that the card is either a 10 or a face card. So for our purposes, a 10 is not a face card. Face cards are only jack, queens, or kings. And so when we do that probability, first we're going to figure the probability that the card is a 10. Okay, so how many 10s are there in the deck? There's 4 of those. 4 out of 52, which reduces down to 1 out of 13. Then we need to calculate the probability that the card is a face card, jack, queen, or king. So there's 3 of those in each suit and 4 suits. So that's a total of 12. So that simplifies down to 3 over 13. So we add those two things together, 1 over 13 plus 3 over 13, and that gives us 4 over 13. And intellectually, this makes sense, right? There's a 10, jack, queen, and king in every suit, so that's 4 in each suit of 13, so 4 out of 13. Our second example is overlapping events, where we have outcomes that are in common. So the same standard deck of 52 cards, and now we ask, what's the probability that the card is a face card or a spade? So how do we know these are overlapping events? Well, there are cards that are both face cards and spades, the jack, queen, and king of spades. So we do this separately. We think first, how many cards are face cards? Well, we know that there's 3 face cards in each of 4 suits, so that is 12 out of 52. How many spades are there? Well, there's 13, because there's 52 divided by 4, 13 cards in each suit. So 13 out of 52. So we add those two things together. There's 25 cards when we add up all the face cards and all the spades. But we also recognize that there's 3 cards that are face cards and spades, the jack, queen, and king of spades. So we subtract off 3 out of 52. So 12 plus 13 minus 3 gives 22 out of 52. So that would be the probability that the card is a face card or a spade. We briefly hinted at the idea of a complement a few days ago in class when we looked at using experimental probability, and we looked at the results of an employment survey. We were asked a question of how many full-time employees were not involved in a certain area. And the way we calculated that is we added up all the different people who were employed in those categories that weren't manufacturing, say, and calculated our probability from that. Well, it turns out that we need to think about this idea of complements, all the outcomes that are not in the event. So If I asked you to name all the numbers between 1 and 10 that are even, you could do that. The complement of that would be all the numbers that are odd, not included in the same event. And when we think about that, that encompasses all the probabilities. They're either even or odd. So 1 minus the probability of an event is equal to the complement of the event. Looking at an example, we roll 2 dice. There's 36 possible outcomes. If we were asked what's the probability of rolling a sum of 10 or less on the 2 dice, well, we could sit down and we could add up all the probabilities of rolling a 2 and a 3 and a 4 and a 5 and a 6 and a 7 and an 8 and a 9 and a 10, which would be fine. We could add those up. But we also recognize that it would probably be a lot quicker just to add up 11 and 12. Those are the ones that are not 10 or less. And then we could subtract off that probability from 1. So there's one way to make a 12, just rolling 6 and 6, and there's 2 ways to make 11, 6 and 5 or 5 and 6. So 3 ways out of the 36. So we would go 1 minus 3 over 36, which gives us 33 over 36, which reduces down to 11 out of 12. So the probability of rolling a 10 or less on 2 dice is 11 out of 12. And the last example is kind of a fun one, and it also involves complement. And we kind of hinted at this a little bit earlier in the year, because I think we actually did have 2 students in a class with the same birthday. So the question is, how odd is that? What's the likelihood that 2 students share a birthday? And so let's say we've got 23 kids in the class. Well, it's a question that's kind of mind-blowing. But what if we approached it from the opposite direction? What if we said, what's the likelihood that no 2 students share a birthday? Well, the first person's birthday could be any of 365 days. The second person's birthday could happen on 364 of those 365 and not be the same. And the third person's birthday could be any of 363 days. And so as we start working our way down that, we find that we're doing a permutation problem. So the permutation of 365 days, taken 23 at a time, divided by 365 to the 23rd power. It looks a little weird. The numbers are huge, but we could consider how this gets put together. When we subtract that off and do that math, we find out that we get about 0.507, which is about a 51% chance. So with 23 students in a room, there's a better than even chance that at least 2 students will share the same birthday. So let's try this out. What's the probability that at least 2 people in a family of 8 share a birthday? So how would we calculate that? So we know that the first person, 1 out of 365. So as we work our way on down, 365, 364, 363, 362, the denominator of our fraction each time is 365, which is where that 365 to the 8th comes from. So the numerator is the permutation of 365 things taken 8 at a time. The denominator is 365 to the 8th. So when we calculate that out, and it's a really huge number, you're going to need a calculator for it, that turns out to be about 0.925. So we subtract that value from 1, and we find out that there's about a 7.5% chance that 2 people in a family of 8 will have the same birthday.